Welcome to week 11. As of now, we have talked about measurement of temperature, pressure, flow and level. Now, apart from these process variables, as chemical engineer, you will also be required to frequently measure important variables such as concentration or composition, density, viscosity, etc. So, in this week, we will talk about miscellaneous measurements such as concentration or compositions, density, viscosity and pH. First, we will start our discussion on measurement of concentration or compositions. We will briefly discuss two important methods. The first method we will talk about is based on chromatography and the second method we will talk about is based on spectroscopy. In particular, we will talk about UV visible spectroscopy. It is needless to mention that for a chemical engineer, measurement of concentration is extremely important. Suppose you want to separate a mixture into given purity. So, you need to know the concentration of the separated streams. You are carrying out a reaction in a reactor, you would like to know the concentration of the products in the product stream. So, the concentration measurement is extremely important for all process engineers. So, today we will start our discussion on concentration measurement or composition measurement. So, these are the miscellaneous measurements we plan to discuss in this week: composition measurement through chromatography and UV spectroscopy, density measurement, viscosity measurement and pH measurement. So, today we will start our discussion on composition measurement by chromatography and we will talk about two methods under this category: gas chromatography and liquid chromatography. We will see that the principle is same for both. Chromatography is a physical process to analyze, identify, separate, purify and quantify a complex mixture. It is a simple and very elegant physical process which you can use to separate a complex mixture and identify and quantify the components. Russian scientist Mikhail Svet invented chromatography during his research on plant pigment. If you look at this diagram, this is known as chromatographic column. The chromatographic column has, say, adsorbent particles in it. This is the complex mixture you want to separate. So, there are more than one component in this mixture. In case of chromatography, this mixture is passed through this column and this column contains, let us say for the time being, adsorbent particles. This column containing particles is stationary phase and we will use a mobile phase which is a fluid. For gas chromatography it is a gas, for liquid chromatography it is a liquid. In this mobile phase I will inject this complex mixture and send that mobile phase through the stationary adsorbent which is there in the column. Now, the components in the complex mixture will have different affinity for the adsorbents or the stationary phase. So, what will happen is at the other end of the column, the components will come out at different times, because the components will interact differently with the stationary phase. So, the migration rates of these components through the stationary phase will be different. So, the components, different components will come out at different times. So, thereby they are separated. So, the components which has very high affinity to stationary phase will take more time to come out, and the components which has low affinity for the stationary phase will come out quickly. We will have a detector at the other end of the column which detects these components that come out. And if I plot the detector response versus time, I will get a plot like this, which is known as chromatography. See, this plot has different peaks, each peak corresponds to different components. So, the time at which these different components come out are known as retention times. Like, so this is the retention time for A, this is the retention time for B, so on and so forth. Looking at this retention time, you can identify the component. Looking at the peak height or the area under the curve, you can determine the amount of the component. For example, the amount of component A is proportional to the area under this shaded curve. So, the chromatography consists of a column which has stationary phase in it. You need a mobile phase. In the mobile phase, you inject the sample mixture you want to separate and identify. The mobile phase is forced to the stationary phase because of the different affinity of the components in the mixture with the stationary phase. The different components come out at different times, so they are separated. We will put a detector here to identify these components and quantify these components. We will see later what are these different stationary phase, what is the length of the chromatography column, what kind of detector I will use, what are the mobile phases that may be used, so on and so forth. So, chromatography is a physical separation method in which the components of a mixture are separated by differences in their distribution between two phases, one of which is stationary, known as stationary phase, while the other mobile phase moves through it in a definite direction. Mobile phase also moves with a specific velocity. The components in the mixture must interact with the stationary phase to be retained and separated by it. Type of interaction may be based on adsorption, solubility, chemical bonding, polarity and molecular filtration. So, these are different types of interactions that the components in a mixture may have with the stationary phase. So, depending on that, we will have different stationary phases. For example, if adsorption is the interaction that is used. We will use solid adsorbent particles, maybe granular solids or maybe granular solids soaked with liquid. It may be ion exchange resin. So, there are different types of stationary phases that are possible. We will see these things in more detail little later. For the time being, let us consider that the type of interactions are adsorption, solubility, chemical bonding, polarity, molecular filtration, so on and so forth. Let us now be familiar with certain terminology used in chromatography. Mobile phase is the gas or liquid that carries the mixture of components through the stationary phase, and the stationary phase is the part of the apparatus that holds the components as they move through it, separating them. A tube packed with stationary phase is called column. So, in case of chromatographic separation, you have a stationary phase and a mobile phase. The stationary phase remains stationary. The mobile phase carries the mixture that you want to separate along with it, and the mobile phase is forced through the stationary phase with a specific velocity. The mobile phase is a fluid. It may be a gas, it may be a liquid. If I am using gas as mobile phase, the terminology I use is gas chromatography. If I am using liquid as a mobile phase, I call it liquid chromatography. So, a liquid mixture can be separated directly using liquid chromatography. A gas mixture can be directly separated using gas chromatography. A liquid mixture can also be separated using gas chromatography, but in that case the liquid mixture has first to be vaporized and then pass through the carrier gas. So, it is the mobile phase that determines whether I am using gas chromatography or using liquid chromatography. In case of gas chromatography, the mobile phase is gas, and in the case of liquid chromatography, the mobile phase is liquid. I will see later what are the different mobile phases that can be used for gas chromatography and liquid chromatography. Retention time, it is the characteristic time it takes for a particular analyte to pass through the system from the column inlet to the detector under set conditions. So, retention time is the time elapsed between the injection and the detection. Retention time depends on the component in the mixture. So, looking at the retention time, I should be able to identify the component. Chromatograph is the instrument employed for a chromatography, and chromatogram is the detector versus time signal. Eluent, fluid entering a column; eluate, fluid exiting the column; elution, the process of passing the mobile phase through the column; flow rate, how much mobile phase passed per unit time, or let us say per unit minute, say milliliter per minute. Linear velocity, distance passed by mobile phase per unit time, let us say per 1 minute in the column. I can express it in terms of centimeter per minute. The primary division of chromatographic techniques is based on the type of mobile phase used in the system. Gas chromatography use gas as mobile phase, liquid chromatography use liquid as mobile phase. Liquid chromatography separates liquid samples with a liquid solvent, mobile phase, and a column composed of solid bits, which is stationary phase. In case of gas chromatography separates vaporized samples with a carrier gas, which is mobile phase, and a column composed of a liquid or of solid beds, which is stationary phase. So, in case of gas chromatography, the stationary phase may be liquid as well as it may consist of solid beds like solid particulate solid adsorbents. Now, let us look at some classifications. These classifications based on type of stationary phase that are used. Gas solid chromatography, the type of stationary phase used is solid underivatized support. Gas liquid chromatography, the stationary phase is liquid coated support. Bonded phase gas chromatography, stationary phase is chemically derivatized support. Gas chromatography is a common technique for separating and analyzing components of a mixture. A given liquid mixture is first vaporized and then entrained by a carrier gas. The carrier gas commonly used are helium, argon, hydrogen and dry nitrogen. The gas mixture is passed through a tube which is known as column in the terminology of chromatography, containing a stationary phase. It may be a microscopic layer of liquid or polymer on an inert solid support. Various components of the mixture travel through the stationary phase at different speeds, which causes them to separate. Since different components emerge from the column at different times, they can be identified by a detector at the outlet of the column. A common detector is thermal conductivity detector. There is also flow ionization detector. A gas chromatography system generates a plot of the detector signal as a function of time. This plot is referred to as a chromatogram. As an analyte appears in the detector, its presence is signaled by a peak. Thus, a gas chromatogram consists of a series of peaks, one for each of the components of the sample. The chromatogram is displayed on a chart recorder or computer screen. So, I repeat, a gas chromatograph system generates a plot of the detector signal as a function of time. This plot is referred to as a chromatogram. As an analyte appears in the detector, its presence is signaled by a peak. Thus, a gas chromatogram consists of a series of peaks, one for each of the components of the sample. The chromatogram is displayed on a chart recorder or computer screen. Different peaks on a chromatogram corresponds to different components, and the areas under these peaks can be used to quantify the mole fraction of each component. So, different components comes at different times. So, detector detects different components at different times, and the detector gives you a response which is a plot of detector signal versus time. So, this plot consists of peaks, various peaks. There will be say 3 peaks if there are 3 components in the mixtures. Now, you should know what is the retention time for these 3 different components, that you can easily obtain by carrying out an experiment with these 3 pure components. So, you know that component A retention time is this, component B retention time is this, so on and so forth. So, you will be able to identify the components. Now, the area under each of these curves. So, the chromatograph will consist of 3 peaks. So, there will be 3 areas under the curve. These areas under the curve corresponds to the mole fraction of these components in the mixture. So, thereby you can separate these components as well as you can quantify these components. So, these are various parts of a gas chromatography. Carrier gas, which is helium, hydrogen, dry nitrogen, argon, etc. You have a flow controller here, so that the carrier gas flow can be regulated. So, the flow rate of the carrier gas must be regulated using the flow controller. Then you have a sample injection system. Now, the sample injection system, depending on whether you have gas sample or you have liquid sample, may be different. So, the gas sample injections and the liquid sample injections may take different forms, because when you have this liquid sample, the liquid sample injection will be followed by the vaporization of that liquid. This sample injection may be manual, it may also be automated. So, in that case it will be a slightly more complex arrangement, but this sample injection system allows you to inject a known specific amount of sample to the carrier gas. This carrier gas now flows through the column. The carrier gas along with the injected sample in it flows through the column. Then at the other end of the column, when the sample comes out, it flows through detector. So, the different components will come out at different times. The detector will generate a signal which is known as chromatogram. Note that there are two peaks, that means there are two components in the mixture. Their retention time is different. So, that tells you which component is what, and the area under these two curves or the two areas that you see, this area as well as this area, are measure of the mole fraction of these two components. So, the main parts are the carrier gas, flow controller, sample injection system, the column, the detector. Common adsorbents are alumina, molecular sieves, silica, activated carbon. So, this is a photograph. These are carrier gas cylinders. This is the column that you see. You have the oven also there, so that the liquid sample is vaporized and passed through the column along with the carrier gas. So, this is what retention time means, the time elapsed between the sample injection and the point of detection by the detector. So, this is a typical chromatogram of paracetamol ibuprofen mixture. Note, the retention time of paracetamol is 2.665 minutes, whereas retention time of ibuprofen is 3.673 minutes. So, this is the detector signal. The area under this graph tells you the mole fraction of the paracetamol, and the area under this graph is a measure of mole fraction of ibuprofen. Of course, we first must calibrate to relate the area under the curve with the mole fraction. So, this is another chromatogram which has several components. So, they have different retention times. Looking at the retention times, you can again find out what are the components are. So, retention time tells you about the identification of the components, and again area under the curve can be calibrated with the concentration or mole fraction of the component in the mixture. So, we will stop here, and in our next lecture we will talk about the more details or the different parts of the chromatograph, a little bit more details, and we will also talk about liquid chromatography.